Okay, the material from this discussion is from section 5.3 of the Zumdahl text. We're going to talk about ideal gases, what they mean, what the term means, and how we use the ideal gas law in calculations. Okay, an ideal gas is one whose behavior is described by our gas laws that we've talked about previously, and it can be explained by kinetic molecular theory. If you remember, we talked about how kinetic molecular theory has 4 postulates to it, and that those are assumptions that are made when we are describing the behavior of this so-called ideal gas. One of them, for example, if you remember, we said that essentially the volume of the gas particle itself is assumed to be 0. We assumed that the particles do not exert any forces on each other. Would be another example of one of the postulates that we had talked about. Well, the thing to keep in mind is, again, these are some assumptions that have been made to explain these laws, and that you never have a gas that, for example, has particles in it with 0 volume. However, the thing is that we can use this concept of an ideal gas to help us describe gas behavior, and that it is applicable under most of the conditions that we see in our chemistry labs. So it's a very helpful model that we can use, even though the assumptions that it makes, seem kind of extreme. But under most conditions, these gas laws and the kinetic molecular theory does a pretty good job. And we'll talk a little bit later about, well, what do we do if we're outside of those bounds of where it applies? And but the thing to keep in mind is, unless we're at very low temperatures or very high pressures, then usually we get pretty good results by using our gas laws, applying the kinetic molecular theory. All right, the ideal gas law. Essentially, it is an equation of state for a gas, as opposed to our Boyle's law and Charles' law, which, if you remember, when we were applying those, we were talking about, well, if I have a pressure and a volume, and I change the volume, what happens to the pressure if the temperature is held constant? We had something changing in those problems. And with ideal gas law, though, it is what we call an equation of state. In other words, it is describing a set of conditions about a gas at a particular time. Okay, we're not really changing or one thing or the other. But so here's our ideal gas law, and we've talked about that before. Okay, and here's description of our variables in there. R is our proportionality constant. It is the universal gas constant, and it is 0.08206, and the units are liter atmospheres per degree Kelvin per mole. Okay, what that means is that when I use the other variables, pressure, volume, and temperature, then my units have to match up to the units that are found in this constant. So whereas with the other gas laws, we just had to make sure we used consistent units, with the ideal gas law, these specific units are required in order to be able to use the 0.08206 value for R. Alright, so we're going to just step through some basic kinds of problems that you'll see. Some of them are basically just plugging numbers in. You'll be given 3 of the 4 variables, and you'll be solving for the unknown one. So let's just look and see, what do we have here? Well, it says we have 56 grams of nitrogen. Remember your diatomic molecules. When we're dealing with gases, if it talks about nitrogen or oxygen or the halogens, that they are diatomic. And it says we have a volume of 20 liters. We have a temperature of minus 73 degrees Celsius. So that's going to be 200 Kelvin. And it wants to know what the pressure is. Okay? So I have a volume, I have a temperature, I want pressure, okay, but I need moles, okay? But I know what my substance is, and I have a mass. So I can get, and I'm just going to use rough estimates here, 28 grams of nitrogen in 1 mole. So that is basically 2 moles of nitrogen. So I'm going to plug them in. Pressure times 20 liters is 2 moles, 0.08206, and that's liter atmospheres per moles Kelvin, and then times 200 K, which is our temperature. So that gives us a pressure equal to 2 times 108,206 times 200 divided by 20. So I'm getting a pressure of 1.64 atmospheres. Okay? All right, now, there's another one that's kind of, let's look what we have. We have a volume there. I have a temperature. Standard temperature is 273. I have standard pressure, which is 1 atmosphere. And the question is, how many molecules of nitrogen? Okay, I have a volume, pressure, temperature, so I can find my moles. So 1 atmosphere, 44.8 liters is N. That's what I'm trying to find. So my number of moles is divided by 0.08206 divided by 273. So I'm getting like 1.9999. So we'll say it's around 2, approximately 2 moles, and 2 moles of nitrogen. 1 mole is 6.02 times 10 to the 23rd molecules. So that is 2 times 1.2 times 10 to the 24th. Okay, now that's one way you can solve this. And one of the nice things about these gas problems is that there's often more than one way to come to the correct answer. Here, what I want to remind you of is what we call the standard molar volume. And I mentioned it before, but we really haven't used it. Standard molar volume says that at STP, 1 mole of any gas is equal to a volume of 22.4 liters. So let's look and see how we could use that, because since we are at STP, how we could use that in this problem. It says I have 44.8 liters, all right, and the standard molar volume is a conversion between liters and moles at STP. So 22.4 liters is 1 mole, and again, doesn't matter what mass. That gives me 2 moles, which, as you saw above, would be equal to 1.2 times 10 to the 24th molecules. Okay, so two ways that you can approach it. You can always PivNerd it and get the correct answer, but again, it can save you a little bit of time if you remember that at STP, 1 mole of any gas is 22.4 liters. All right, now Another variation on these Pivnert problems is where they're going to give you the information maybe not so directly and ask you for something that's not straight out of the equation. For example, molecular mass of a gas. This is a real common one that you'll see. And the key thing to remember in these types of problems is think about the units of what you're trying to find. Okay, so molecular mass of a gas, what you want to think about anytime they ask for that is think about, okay, that is grams over moles. Grams per mole. So, and then think about those two things separately. In other words, look through the information given. In this case, do I have grams of something somewhere? Or do I have moles, or do I have information where I can find moles? So in this problem here, we look and we see that we do have grams. It's not a straight out mass, but it's embedded in this density. And so what that says is that if I have a volume of 1 liter of this gas, it has a mass of 0.16 grams. So I can use, for my molecular mass, I can use this 0.16 grams as long as when I find how many moles that is, I use a volume of 1 liter, okay, because this is 0.16 grams per 1 liter. All right, so let's go down here. I have a volume of 1 liter. Temperature is 25 degrees C, which is 298 Kelvin. And I have a pressure of 745 torr. All right, to Pivnert it, I need it in atmosphere. So I'm going to convert it. And that's going to give me 0.98 atmospheres. Okay. So if I put that in, so I get 0.98, 1 liter, 0.8206, and 298 Kelvin. So 0.98, 0.08206 divided by 298. So I get 0.04008 moles. All right, and that value is what I'm going to use right here. Okay, so we'll carry the calc over here. 0.16 grams divided by 0.04008 moles gives me a molar mass of 3.99 grams per mole. Okay, so this is most likely helium. Okay, so there's that kind of a problem. And then here's another one. Here it's asking us to find the density of carbon dioxide at 40 degrees Celsius and 1 atmosphere pressure. Again, look at what the units are going to be. I need grams of CO2 over, it doesn't say if it wants milliliters or liters, so we're just going to do grams per liters of CO2. Okay, so now, again, look at these separately. Do I have grams? Can I find grams based on anything that the problem gives me? You know, can I find liters based on anything the problem gives me? Well, it's given me a temperature. Okay, and it's giving me a pressure. And I'm trying to find a volume, which means I need moles. All right, so let's go back up here. So I'm kind of stuck right there, but then look here. I know that it's carbon dioxide. if I know what it is, I know what its molar mass is. So carbon dioxide has a molar mass of around 44 grams per mole. That's the number of grams in 1 mole. So I can use 44 grams in my density calculation if I get the amount or the volume, if I get that using 1 mole. Alright, so again, piv inert, we get 1 atmosphere. V is what I'm trying to find. I'm going to use 1 mole, 0.08206, and 313 Kelvin for my temperature. That gives me a volume of 25.7 liters. And so that's the value that I would plug into the denominator. So my density of CO2 is going to be 44 grams divided by 25.7 liters, which would give me 1.71 grams per liter. Okay? Now, the last slide I have for you, here are some practice problems that are just like the ones that we went over. Kind of gives you the types of problems you can expect to see where you're just using the ideal gas law. So try your hand at these. If you're not able to get the right answers, then come into class tomorrow with some questions.